So this is an important session for the Society. As many of you know, the Society takes great pride in awarding PhD theses and outstanding young colleagues. This is done through a nomination process where people submit their nominations, and the President appoints a committee that evaluates each nomination. And once they make a decision, they are announced. Before 3 years, we used to offer the PhD awards only once every 3 years, but since the field is growing, we have now decided to offer it every year. So that is the reason why you see 3 PhD awardees here. And this year we also had an unusual but a good situation that the committee decided that we'll have a joint winners for also the Young Scientist Award, essentially. That is for a young scientist with outstanding publications. At this point, I should also thank Paulo, Alexandra, and the organizing committee for waiving the registration fees for the award winners. And the Society supports them through a prize award and also some a travel grant. So it is, I'd like to make 2 points. Colleagues that you have, students and young researchers, please nominate them. Only if they get nominated, they get considered, so please nominate them. It's a fantastic opportunity. And the next one is for all the awardees. With great awards comes great responsibility. So we look forward for your continuous support to the Society and to pay it forward to other young people. So please engage yourself with young people. They really look up to all of you as future leaders in this Society. So we move on to the next class of our award winners. This is an award for outstanding publication by a young member of the Society. We have the first joint winner, Kurtis Carsch. He runs this independent group. He's an assistant professor at the University of Texas at Austin. Kurtis, over to you.
Thank you very much. Is this the advance? Awesome. So my name is Kurtis Carsch. I'm a new assistant professor at the University of Texas at Austin, thinking about solution processable materials. And I'm excited to have the opportunity today to showcase some of my research from my postdoc with Jeff Long at the University of California, Berkeley, where we've discovered this exciting new class of adsorbents that can operate at these really extreme conditions that have never been approached before by adsorbents. And the motivation for our study entails that we as a society work with materials that are produced at high temperatures. We can think about taking crude reagents that we extract from the ground, and then through some type of high temperature valorization, we can isolate desired commodity chemicals. Now, there are some inherent challenges with this process. One is that many of these reactions require elevated temperatures, at which point we're going to likely be pursuing combustion to access those temperatures, which is going to be emitting carbon dioxide in that process. A second challenge is that many of these reactions that are societally important and not going away anytime soon inherently have carbon dioxide on the right side of the equation. So 2 reactions that we can pick on here entail cement manufacturing, the thermolysis of calcium carbonate. This is going to make calcium oxide and carbon dioxide, as well as steel making, which is the reduction of iron oxide with carbon monoxide. So every time you run these reactions, you are inherently going to be making carbon dioxide, which is going to be a challenge as we're trying to move toward a more carbon neutral or carbon negative world. And so there's a question of why don't we simply just capture the carbon dioxide that comes out of these processes to avoid emissions from these processes. And I have displayed on this slide the largest post-combustion carbon dioxide capture plant in the world, which is the Petronova plant out of Houston, Texas. Shown here, we have these carbon capture units that work with aqueous amines, but the challenge here is that there's the discrepancy between the temperature of the combustion process and the temperature of capture. So to be able to capture with aqueous amines, we need to drop the temperature of the flue gas below the boiling point of water. And to do that, we're going to use water as our cooling system. And as displayed on this slide, we have these large cooling towers with these large smoke plumes that reflect the water vapor escaping the system. So effectively, we are actively bringing in water into our setup so that we can cool down the gas so we can undergo capture mechanisms. And unfortunately, one of the defining features of the 21st century is water scarcity, where being able to do post-combustion capture will entail a large water penalty. I have displayed here a map of the Globe does study from Berkeley Sustainability School, where they came to the conclusion that many countries in the world, many regions of the world, are now facing water scarcity, where simply put, shown here in red, there are not enough atoms of water in California to be able to meet the demands that California needs for carbon capture. So if we can't undergo carbon capture at modest temperatures associated with aqueous amines, we need to be thinking about capturing carbon dioxide at temperatures more associated with the emitted flue gas. And this is quite a developed field in terms of absorbance. The idea of using absorbance for high temperature CO2 capture is quite well developed using processes such as metal oxide looping. And what I have displayed here is a relatively high technology readiness level technology known as calcium looping. We can start with flue gas and heat it up slightly to be able to undergo carbonation of calcium oxide, my apologies. And then we can separately take that now formed calcium carbonate, thermalize it in a higher temperature secondary vessel, and that can give us a high carbon dioxide flue gas effluent that can then be subsequently stored. Well, the challenge with using an absorbent in this process is that we're undergoing large volumetric changes between the oxide form and the carbonate form, such that we're going to undergo this inherent sintering problem, such as we start cycling, we're going to be losing some of that macrovoids, which is going to make it more challenging for carbon dioxide to diffuse into the interior of these materials, which is going to limit greatly our kinetics of adsorption. Now, one of the challenges here is that sintering is a direct consequence of the large volumetric changes between the oxide and the carbonates. Excitingly, when we think about porous materials, such as metal organic frameworks, we may be thinking about single-digit % changes in the overall volumetric expansions, which can help avoid some of these sintering problems. Unfortunately, the majority of metal organic frameworks operate through physisorption. I have shown here plots at variable temperatures of gas carbon dioxide binding to the open coordination site in magnesium MOF 74. At modest temperatures of 20 degrees Celsius, we have steep uptake. We have a lot of carbon dioxide that is binding to this Lewis acidic metal site. But the challenge is, as we increase the temperature, we are going to make binding more entropically penalized. And you can see here, these isotherm profiles start flattening out as we go from 20 degrees Celsius to a harsh 200 degrees Celsius. And really, at the start of our work, this was the state of the art for adsorbents performing at high temperatures. So we thought about this process from a simple energy perspective. If our Gibbs free energy is penalized by our entropy of adsorption, we need to offset it with high enthalpy of adsorption. And in our interpretation, we thought about that as CO2 functionalization can provide sufficient enthalpy of bond formation to overcome this entropic penalty. And we thought about one of the simplest reactions, which is the addition of a hydride to CO2 to produce formate. This is an extremely common reaction, and I'm trained as a molecular synthetic inorganic chemist. And this is actually an easy way that our community tests for hydricity and the presence of a hydride. Simply, can you make a metal hydride, and can you react it with carbon dioxide? And our excitement here was this idea of potentially we could render this reaction reversible and then use this reversible metal ligand bond insertion as a mechanism to be able to undergo gas capture. So the framework that really excited us was one known as Metal Organic Framework OLM4 Large, discovered by Volkmer and coworkers. It's a relatively straightforward framework to make. You just take commercial zinc dichloride, you take this dibenzodioxin linker that can also be commercial now, and you simply combine them at elevated temperatures with some solvent, and out comes this three-dimensional framework known as MFU4L. And what's really exciting about MFU4L is that when we zoom into the node, we have this pentanuclear building block, where in each pentanuclear building block, we have these 4 terminal zinc chloride sites, where we can do synthetic chemistry at those zinc chloride sites and start dialing in electronic structure by changing out the anion or changing out the metal ion. And what we're going to do here is a series of post-synthetic elaborations to change out this chloride here for a corresponding hydride ligand through intermittency of a formate ligand that can undergo an elevated temperature decarboxylation. We can resolve the hydride in the difference map using single crystal X-ray diffraction, but we can also use neutron diffraction and also validate the presence of a hydride using a difference map with infrared spectroscopy. So we can decorate this material that has a very high affinity of, a very high loading, of metal hydride sites that could potentially be used for carbon dioxide binding. And when we went in the lab and explored this material's affinity for carbon dioxide, we were actually quite confused. We can load this material up with carbon dioxide, and we can unload it with carbon dioxide without seemingly any high capacity or high evidence of insertion. We're looking at gravimetric capacity, where our y-axis here is going to be our capacity of CO2 as a function of the mass loading. And our x-axis here is going to be loading, those are the colored in circles, and then unloading CO2, those are the open circles. And potentially what we had thinking was that there could have been a barrier for this insertion chemistry to occur, at which point maybe we actually needed elevated temperatures to be able to turn on the desired chemistry. Well, with some engineering to be able to run these measurements using a furnace, we actually saw that when we increase the temperature to 150 degrees Celsius, we now have a very different isotherm profile. Now we see something that is steep, that actually reflects that for every zinc hydride we have in our structure, we have one molecule of CO2 that is now chemisorbed. And excitingly, when we go above 200 degrees Celsius, we have a process that is fully reversible. Simply by changing the pressure, we can load CO2 on this material, and then we can unload CO2 on this material. And we have something that is quite remarkable. This is the first adsorbent that can actually operate with high capacities at these elevated temperatures, where we have fantastic affinity for CO2 based on chemisorption, and we have no affinity for other gases that may be present in the stream. We can then undergo breakthrough measurements at these elevated temperatures. We can see that as we go from 20% CO2 to 4% CO2, we increase the breakthrough time. Or another way of putting it, it takes longer for our adsorbent to saturate. Where we have deep capture, as we're capturing all the molecules of CO2 until our adsorbent starts to reach saturation. Well, this is quite a remarkable material. We can take our zinc hydride, expose it to CO2, and it makes a zinc formate species. We can capture CO2 from air at elevated temperatures. We can capture at 400 degrees Celsius. We can tolerate water vapor at 200 degrees, although above 200 degrees, this is the current limitation of this material. And we can tolerate oxygen and SO2. And once we make this zinc formate material, simply by elevating the temperature and dropping the pressure, we can strip this material of CO2. And that's something that we're really quite excited about. And then we can use computations to try to understand the unusual mechanisms of this material. And what we actually find here is that in this transition state for CO2 insertion, the hydride is the nucleophile, the CO2 carbon is the electrophile. There's actually this geometric distortion where the hydride of the zinc hydride has to cant into the ligand, and that actually gives rise to a large penalty such that we need these elevated temperatures to actually undergo the insertion process. And this is quite fantastic. We have a process that has a barrier, and then it is slightly favored at elevated temperatures such that the reaction does occur, but it is a reversible process. Well, if we're thinking about decarbonation of steel manufacturing, it's not just removal of carbon dioxide we have to think about, it's also removal of carbon monoxide. And in some unpublished work that I'm quickly going to walk through, we were quite inspired by this idea of overcoming cryogenic distillation to remove carbon monoxide based on some molecular inspiration that copper-1 systems will have a high affinity for pi acids, such as carbon monoxide. Well, shown here are elevated temperatures, isotherms, of a metal organic framework that contains copper-1 sites that has a high affinity for carbon monoxide, completely reversible at 290 degrees Celsius. The binding affinity is about 110 kilojoules per mole. We can load carbon monoxide, and then we can unload carbon monoxide. And what's exciting here is we can also undergo near-perfect selectivity of ethylene-ethane of separations. This material is actually selective for ethylene over propylene because we are targeting the pi acidity, not the polarizability. And that allows us to undergo pi acid separation. So we can also undergo breakthrough measurements at elevated temperatures. Apologize for the noise, but effectively we have something that can select out for carbon monoxide from something that is a mixture of oxidative coupling of methane. So let's put these two frameworks together, our metal hydride and this copper-1 metal organic framework. We can cycle these using thermogravimetric analysis measurements where we can load the gas and then unload the gas. And then we compare these together to what's being considered a dream reaction or a dream separation, where you can take something like blast furnace gas at elevated temperatures, and without having to undergo complicated transfer of heat, we can simply strip out the carbon dioxide, the carbon monoxide, and then undergo subsequent valorization of these chemicals, where we've been able to retain that heat energy for subsequent processes. Ultimately, I've had a fortune and a very joyous time to work with this large lab and the Long Group to be able to target some of these highly ambitious and exciting projects. I'd like to particularly thank Jeff for his mentorship, as well as Rachel Brody, who has been a co-author on these projects. And I'd be happy to take questions.
Great.